So now I want to talk in some more detail about a topic that I've mentioned a number of times throughout these series of lectures, and that is fractographic analysis. And what I really mean by that is looking at a fracture surface, measuring some of the features on a fracture surface that give us a great deal of information on what caused the fracture. In other words, what kind of defect was it, or what kind of scratch was it, how big was it, but also can tell us a lot about the stress at fracture. There's quantitative aspects of features found on the fracture surface that are very important and are not always used to the greatest extent they could be in understanding what's going on in the fracture process. For the kind of the Bible of fractography, I recommend this NIST practice guide written by my colleague George Quinn. He probably is today the world-recognized expert on fractography of ceramics and glass. And this contains a myriad of details into how to do fractography. I will show you some of the things you can learn from fractographic analysis. The Guide to Practice teaches you a lot about how you should be carrying out these studies and some about what you should be looking for. So I heartily recommend this to you. It's available on the web to download for free. And if you have any interest or any work going on in fracture of brittle materials or other materials as well, I strongly suggest you go take a look at this. So in this lecture, will only talk briefly about how one does this kind of thing. First of all, it's very easy to look at the macroscopic aspects of fracture in the first degree. And you see here on this picture a glass plate, and you can pretty well see that fracture occurred from this region in here, and then the other cracks grew out of this at some point, or secondary crack growth that happened. So in all of your aspects of looking at the fracture surface, the macroscopic aspects are the one you should look at first. Now, glasses, as I said, are particularly easy. There's a lot of work been done. It's much easier to find the fracture origin in glasses than in many polycrystalline ceramics, where the existence of microstructure interferes with our ability to see the boundaries of the original flaw. But in most materials, with some experience and right practice, it can be found. What I want to particularly talk on in the beginning here are these 5 regions of crack growth that you see shown schematically in this diagram. As the crack grows out from the origin of failure, from the original flaw, it moves through these and leaves fracture markings corresponding to these 5 regions of crack growth. So the first one is the flaw itself. The semi-elliptical flaw that I talked about from the beginning that exists on the surface, most likely due to some machining or grinding or polishing operation. Sometimes that's the easiest one to see, sometimes it is not, depending on the microstructure of the material, how severe the flaw was, et cetera, et cetera. But in most cases, it's the one thing that we need to see. What kind of flaw was it? Was it an inclusion? Was it a real crack? And so it's important to be able to find that, because once you find that, it's much easier then to go through and find the other regions of crack growth. The next region, and this is one which is always seen in glasses, but is much more difficult to see in polycrystalline ceramics, is what we call the mirror region, and with good reason. It's a very smooth, shiny region in glass in which the crack is moving relatively slowly. I say relatively. It has probably achieved criticality and failure will occur, but until it reaches a certain velocity, it's at a velocity at which no other cracks are formed, and so there's this smooth region through which the crack traverses. The next region that happens is called mist. This, you can see in here, I think, a little dotted region that you see here. This is where secondary cracks begin to grow, because the crack velocity is such that the energy I'm inputting to the specimen is so large that the main crack itself cannot achieve a higher velocity, so some of that energy goes into the formation of mist, that is secondary cracks that only begin, and so it's a stippled area that you see like here. But there's usually quite a distinct boundary between the mirror and the mist, and there's the secondary boundary called hackle, which you see in here, where now there's even more energy, and those little cracks that you see in this mist region are grown to a larger size, and you can see those in this regime here. And then finally, you get macroscopic branching, and what you saw on the original picture I showed here is where the crack actually has branched and formed a lot of secondary cracks. Sometimes it forms only two, sometimes it forms many, depending on the stress state. I should point out further that depending on the size of the specimen and the stress level at which failure occurred, you may or may not see each of these regions. If the specimen is too small, then these cracks grow into a compressive region instead of a tensile region, and you won't see all or part of all these regimes. So one must realize that it's going to be material dependent and stress state dependent whether I can visually observe each of these regions. And the way to look at them, for the most part, is in optical conditions. A stereoptical microscope works best. Again, refer to the Quinn Guide to Practice. Use one for adjustable lighting, and again, there's a lot more detail available out there. And give you an example. I think I showed it briefly earlier. So here's the original crack, and I think you can begin to see where there's a mirror region out here, and then you can see a little bit of mist and some hackle out here. So it turns out the size of the mirror, the size of the mist, and so forth are very dependent, in fact quantitatively dependent on the stress at fracture, which is an important aspect of them that gives you a lot of data about the way fracture occurred and the stress at which it occurred. Here's an example in a polycrystalline material, yttria stabilized zirconia, where now you can see these regions, but the boundaries are much more difficult to discern. The boundary regions are a little more vague. You can see, though, that you can find these if you look closely. Again, it's much easier in the actual microscope than it is on a picture. Further example on a dental material, where again you can see the origin and pieces of some of the other behavior that you see here. Just to point out that there are internal failures that are observable. Here's a silica nitride in which failure occurred from an internal origin. And again, even though it was internal, you do see these mirror in here and mist and hackle regions within the micrograph itself. So stressing there's a lot of information to be learned about what happened at fracture, about the stress at fracture, if you take the time to look. What I want to point out is there's a quantitative relationship. These aren't just qualitative boundaries, they are quantitative boundaries. And they give a lot of information about the stress at fracture as well as maybe the cause of fracture. These boundary constants, they're called mirror constants, are actually stress intensities at each of those boundaries. And as it turns out, the fracture stress multiplied by the radius to the particular boundary, where J represents either a mirror, mist, or hackle boundary, is related to the stress intensity factor, with including this geometry factor Y for each boundary. What does that tell me? It says that if I can find the boundary in a part that failed in service, I can know the stress at fracture. If I take the time to take that same material and actually measure these mirror constants where I have a known applied stress, in other words, I go to a test machine and I do a series of specimens, fail them in some load, I will get the boundaries and I can calculate these mirror constants. For an unknown failure, I can then use these mirror constants to determine, by measuring the boundary itself, what stress caused failure in my component. A very important aspect of fractography, which I think is probably not used as much as it should be. I should also point out that here's some examples for silica, but that these relationships are valid all the way from glass fibers to macroscopic specimens. So it didn't matter what the size of the specimen was, the mirror constant for that material is constant over a wide range of sizes. So it really is more or less a material constant, and which makes it particularly useful. So the size of the component, if I can find the mirror boundaries, give me a lot of information about the fracture behavior of the material. Another aspect that I think is important is that there's the residual stress or lack of residual stress in the component can be determined by measuring the strength mirror size relation in that material. So if there's a macroscopic residual stress, say because I didn't fully anneal the glass, for example, then what it does, instead of a curve that looks like this, if I plot versus 1 over the radius versus the strength, I get curves that have the same slope, which are displaced because of the degree of tempering. So you can see that there's completely annealed glasses, they pass through the origin. If I have some degree of macroscopic residual stress in the glass because I didn't anneal it, then what is called tempered here, then it's displaced. The curve is displaced by some amount, and that's equal to the amount of residual stress left in the glass. So that again is a useful piece of information. I should point out also that residual stresses local to the initiating flaw can cause changes in the fractographic analysis. They will change the shape of the fracture mirror, so it can go from semi-elliptical in one direction to almost semicircular or vice versa, and will change the mirror constant as well. So you have to be aware that these so-called local residual stresses affect the fractographic analysis in a different way than the macroscopic residual stresses I just mentioned. One other interesting aspect are the effects of slow crack growth. We talked a great deal about the importance of slow crack growth. That is, failure doesn't have to occur instantaneously, but can occur because cracks grew over a long period of time. I won't go into detail on these curves, but the major point is brought out up here, that the mirror constant, those A values that we saw earlier, were unrelated to the time it took to cause failure. So whether the part failed instantaneously or failed after a period of time under load, the mirror constant stayed the same. So if I have a part that fails after 6 months in use, I can tell what stress it was under, even though failure did not occur immediately upon application of the stress. And that can be particularly important for analysis of undesired failures in the field. And more or less, this is what I say here. So the stress at which a failure of a part occurs can be determined from the fractographic analysis with knowledge of the mirror constant, regardless of whether it breaks instantaneously or after a period of time in service. So it goes back to the point that if you're making large numbers of parts that are likely to see stresses in the field, it would be valuable to determine the mirror constants for that material, because later on it gives you another tool to analyze whether there was an overstress at some point, or whether it simply failed because cracks grew slowly with time under the load that you expected. It gives you another possible piece of information. It's a materials property that can be determined reasonably easily simply by going into the laboratory and measuring mirror constants as a function of stress on flexural specimens, for example. So summarizing, I think there was only one short message, is that it's a powerful tool to understand the cause of fracture and the determination of the fracture stress. I spoke earlier about the need to do fractographic analysis to determine the cause of failure, whether it's an inclusion, a different shape flaw, a different size flaw, in order to understand the statistical nature of the failure origins. But it can tell you a lot more. It's much more quantitative in nature, and so gives you a lot better information about the stresses in the material and some guidance as to whether there was a problem with the material or an overstress due to some phenomenon that you were not predicting.